Alright, let's do some more areas. This time it's a classic question. Find the area that lies inside some curve and outside some other curve. So here, this curve is the limits on here on the side. This curve over here is a circle. R is equal to 4. We're trying to find the one inside the outer one but outside the little one. That would mean this region right here. So here we can highlight them. That area right there, the greenish area, that's the one we're trying to find. That's inside this curve but outside R equals 4. So the standard procedure is to slice it up into infinite many little pieces. Let's go with red this time. So we slice it up into infinite many sectors such as this, and now we have a shape that looks, roughly speaking, like this, and we're trying to find the small little area of such a shape. Well, that area would be the same as the big sector minus the little sector. That would give you the just that portion of the sector. So this would be equal to, we discussed this before, this is big R, this is little r. So this would be big R square over 2 d theta. This one would be little r over 2 square d theta. So often people just write like this: 1/2 r square minus r square times d theta. That gives you the area of a shape like that. There's not really any formulas to memorize, just common sense. As long as you know that the area of a sector is the radius squared divided by 2 times the angle in radians. Alright, so that's the deal here. Now we're going to add them all up. We're going to add them all up using the grace and elegance of the fundamental theorem of calculus. And we need theta limits. So I'm going to need to figure out, this is my starting point, theta at start, and then I'm sweeping. There's a whole bunch of these. These are all stacked up. All the right ones are stacked up all the way up to here. So this would be the end. So the sectors are piled or stacked up right next to each other throughout this entire region. So we should find those angles. Now to find those angles, you should make note of what characterizes those points. These points are characterized by the fact that the two r's are equal to each other. That r intersects the other r. So here, make a little box here. Let's find some limits of integration here. R is equal to 4 on the one hand, and the big R is equal to 5 minus 3 cosine theta. At this point, they meet. At that point, they are equal. So 4 is equal to 5 minus 3 cosine theta. Therefore, negative 1 is equal to negative 3 cosine theta. Therefore, 1/3 is equal to cosine theta. Therefore, I've got a cosine graph here. Cosine graph goes like that forever. And I've got a 1/3 graph. 1/3 is somewhere around here. And I've got a whole bunch of points where they intersect. And I bet you this one is the one that's here, a little short to 90. That would be that one right there. You see, this is 0, this is 90 degrees, this one's short of 90. This is 0, this is 90, this is short of 90. That's the one I want right there, the first one. And the other one would be the one that's right before I get to 360. This is 360, and I'm going here all the way over here, all the way to 360. But well, all the way to 360 would be all the way over here, but I'm short of 360. That's probably the other angle I get, the other angle I want. These are all the points where the two curves intersect. So talk is cheap. Let's do it. I bet the calculator can give us the first one. So I do a cosine inverse of 1/3, and that's equal to, where's my calculator? I'm getting that's equal to 1.27. 1.27. 1.27 radians approximately. What does that make this one? Well, that would be 2 pi minus 1.27. So that's about 6.28 radians. Take away 1.27. I don't know. Let's use the calculator again. That would be approximately 5.05 approximately. So my limits are from 1.27 radians up to approximately 5.05. And so I have a nice setup now. The setup goes like this. I'll do the setup in green. So I've got that the area is equal to a half times big R squared. So that would be 5 minus 3 cosine theta squared minus, I'll just do it separately, a half times little r squared. So that would be 4 square. All that is times d theta. And my limits are from 1.27 radius, that's the one that's a little bit short of 9 degrees, to 5.05, that's short of 2 pi, which would have been 6.28. And now the rest of this is just grunt work. All we have to do is crank this out and we'll be done. I'll draw a few more lines here. Let me get this out of the way just so we have more room to work with. This will be a half. Of course I've got an integral still. 25 minus, that's 15, times 2 is cosine theta plus 9 cosine squared theta minus a half times 16. And this is all going from 1.27 to 5.05. Okay, and that becomes, of course, a half times 25 minus 15 times cosine theta plus 9/2 times cosine squared. That's a half plus 9/2 times a half times cosine of 2 theta minus a half times 16 times d theta. And of course that becomes half times 25 theta minus 15 sine of theta plus 9 over 4 theta plus 9 over 4 times sine 2 theta times a half minus I got a half times 16 times theta. Can't see that, huh? Let me slide it over just a little bit. There. So now what? Of course all this was from 1.27 to 5.05. So the limits here you have to evaluate from 1.27 to so call this f of theta. Now the answer is f of 5.05 minus f of 1.27. And that's it. You're done. I'm not going to plug it in there. That stuff is not that interesting. But you would plug in there, this is theta by the way at the end. You would plug in 5.05 and then 1.27 in there and you'd get the answer. Very nice problem. Few nice ideas. You don't have to memorize anything. It's just common sense. Probably. Anyways, take a look at it. See if you can finish that, and that's a good area. Alright, I think that we have one more thing we should talk about, and then we can wrap things up. What we should talk about now is arc length. So why don't we set up one or two arc length problems in polar coordinates and see how that looks. Alright, we'll do that and then we'll call it a day.